Hello class. So let's start on 5.2, orthogonal complements and orthogonal projections. So let's actually start off, before I give you the definition here, if you'll remember right, when we were, here we are, early on when we talked about null spaces and the subspaces right at the beginning, and the row space and the column space, I brought to class this Geogebra Applet. And let me remind you what we have here. So these blue vectors, they are the row vectors. So the matrix, if you look at this spreadsheet right up here, this matrix 1, 2, a negative 3, a minus 1, 2, and 5. So if you plot 1, 2, and a negative 3, and a minus 1, 2, and 5, those two vectors are these black vectors. And if you row reduce, then you get two other vectors. And remember, we had a theorem that said if you row operations don't change the row space. They might change the column space, but they don't change the row space. And the red vectors are the row reduced ones. And if we look at from the top, like the red vectors, you can see they line up with in an x direction and a y direction. They're off by a little bit. Oops. Yeah, so right from the very top you can see that they line up with the x and y coordinates, but z coordinates, they still have some component in the z coordinate. And the null space to of a matrix is it's a vector that's perpendicular to the row space, or it might be a plane that's perpendicular to the row space, or however many dimensions you have, it's perpendicular to the row space. And this is the kind of geometry we're going to be talking about today. So if you have a subspace, like this blue plane, then the column space, not the column space, the complement, the orthogonal complement to that plane is all of the vectors that are all of the vectors that start at the origin that are perpendicular to that. So if here, since we have a plane that goes through the origin, it's a subspace, and the orthogonal complement it's all the vectors that go through the origin that are perpendicular to that plane. So this line that goes through that purple, come on, I can't, it's not letting me do it's not letting me show it, I'm sorry. If we were to extend that purple null, the purple vector that says null space basis in a line that goes out and back, look at the span of that line, all the vectors on that line would be the orthogonal complement to the blue plane, that light blue plane. Okay, and it works the other way around, that if the subspace we had was the line that went through the origin with that purple, that if we extended that purple, look at the span of that purple vector, then the orthogonal complement is the plane that goes through the origin. As in total, you're still going to have n dimensions between your basis and your orthogonal complement to your basis. So I'm sorry, yeah, you're still going, you have to fill up everything. So if we're in R3 and I've only got a single dimensional basis here, single dimensional subspace, then the orthogonal complement is going to be two-dimensional. So, and then because I have one dimension in one, two dimensions in the other, it'll add up to R3. Okay, so this is the kind of geometry we are talking about. And this will build up to one really important theorem also. Let's get back to not that one. Okay, so if W is a subspace of Rn, then a vector U is said to be orthogonal to W if it's orthogonal to every vector in W. And if we go back to here, so purple, no matter what vector we draw in the plane, that blue plane from the origin, it's going to be orthogonal to that purple one. We have 4 vectors drawn, and there's always some way for me to turn this so I can see that it's. I'm really struggling manipulating this without a mouse. There's always some place I can put it and show that it's perpendicular to the other one. We get 90 degrees, but like right there works for all of them. So there we go. So to be orthogonal to a plane, not just, so we've talked about 2 vectors being orthogonal, but to be orthogonal to a plane, a vector has to be perpendicular to all the vectors in that plane in standard position. So, okay. And the set of all vectors in Rn, which are orthogonal to W, is called the orthogonal complement of W, and is denoted as W. Then it has a subset on T that's supposed to be 2 line segments, or 2 lines that are perpendicular. So like that's supposed to give you like the 90 degree idea there from geometry. And then so now we've already talked about these. If you've got a line in R3, what is the orthogonal complement of the line? It's going to be a plane through the origin that's perpendicular. This should be a line. It should have said a line through the origin in R3, because that's the only place you're going to get a subspace. We're talking about subspaces here. So the line, for it to be a subspace, has to go through the origin. And with a plane in R3 that goes through the origin, what's the orthogonal complement? It's a line that's perpendicular to that plane that goes through the origin. So we kind of looked in GeoGebra to talk about that already. So here's a few things about orthogonal complements. So if W is a subspace, then the orthogonal complement is also a subspace. If it has the 0 vector, because the 0 vector is perpendicular, is orthogonal to everything. What are other things we need for the subspace? If you take two vectors that are orthogonal to W, and you add them together, they will still be orthogonal to W. It'll create a vector that's orthogonal to W. So what we're doing is we're talking about subspaces right now. And if you remember, we needed 3 things. 1, the 0 vector had to be an element of the subspace. 2, U and V, if U and V are elements of the subspace, then U plus V is in the subspace. And that works for these 2. And if U is in the subspace, then C times U, where C is a constant, is an element of the subspace. By multiplying by a constant, a vector by a constant, if it's already orthogonal to a plane or to a line, it's still going to be orthogonal. So, okay, so that's what that first one's saying. The orthogonal complement to the orthogonal complement is the subspace. So if you look at all things that are perpendicular to W, and then you look at all things that are perpendicular to the things that are perpendicular to W, you just get back to W. So the only thing that W and W complement share is the 0 vector. And if W equals the span of a bunch of vectors, so that's how we're defining this. You can define a subspace as the span of a set of vectors, right? Then V is in W complement if and only if V is orthogonal to each of these vectors in the span. So it has to be orthogonal to all of those, not just one or a few. and I'll let you study the proofs later. Okay, this is a huge theorem in linear algebra. So big that like they call them these things we're going to talk about. They're called the fundamental subspaces of A. So, and this gets the geometry of this is connected to the GeoGebra image that we used earlier. So this says that the orthogonal complement of the row space is the null space. So we actually saw that the null space of that one. So the row space is this blue. Oh, please work. The row space, the span of the row space, or the row space, which is a subspace, it's already a span. It's the blue vectors. I'm sorry, it's not the blue vectors, it's the blue plane. And the null space of that system, like all, is this perpendicular purple line right there. So that's the basis for the null space, and the null space is the whole line. So, and we can see that they're perpendicular. So that's what that says. We already talked about that in a previous class. We didn't talk about it as a theorem. I was just trying to understand what a null space is. And because the null space is all the vectors that get mapped to the zero space. And, well, we need to keep going. So let's get back to this. And the column space, the orthogonal complement of the column space is the null space of a transpose. So if you transpose A, then your old columns are your new rows, and then the null space of those new rows is the orthogonal complement of the column space. And so we could create a new GeoGebra app with GeoGebra sketch and to look at the column space of A and see what that is geometrically. Sorry, I'm really struggling today. Had a headache most of the day. And then we could show that the null space of A transpose is a set of vectors or a plane that is perpendicular to the column space of A. So here we don't prove this for you, but we just do an example. So x bar, we find an x coordinate, an x vector that's perpendicular to, it's orthogonal to each of these vectors in the row. So notice that, like, how to find these is a little bit different, but we're just telling you, look, this one is perpendicular to this first row, right? If we write that 1, 0, 2, and minus 1, we get it right there. If we dot product with x, we get 0. And same thing with the second row. If we write that down, dot product with x, we get 0. So that means that this vector, this vector x is an element of the row. It's in the orthogonal complement of the row space of A, because it's perpendicular to the row space, to these two basis vectors. It's perpendicular to all of the vectors in the span. And in this case, we only have 2. Because remember, if we go back, then here, if and only the vector is in the complement of W, the orthogonal complement, if and only if it's orthogonal to each of the vectors that are in the span of of all the vectors that you can use to generate that space. So in this case, we only have 2, and it's orthogonal. And so that means, like, it is in the null space of A, because if we do this multiplication, then we multiply it by, we get 0, 0. Because we don't have to do the math again, because when you first do the row and column thing, that is just a dot product, and we already did dot products up there. So do the dot product of the first row and then the vector, which just has one column, we get 0. Same thing with the second one, we get 0. And so it's in the null space of A. And so that's what it's saying. Like the null space of A is the orthogonal complement of the row space of A. This gives us a geometric way of understanding what the null space of A is. I already had brought that up earlier in the class to help us make sense of the null space. So, so here we have a subspace and of W, and here we have, it's defined by the span of these two vectors, and the task is to find a basis for the orthogonal complement of W. Now you could try some things like picking an A, B, C, D, E. Like you'd start by setting up this huge system if you wanted, and dot prodding it with those, and trying to solve systems of equations and making sure that these things would be the dot products with those would be 0. But let's use the power of the theorem that we have, because it already says that if we want the orthogonal complement of W, then we just have to find the null space of this system. At least so the null space where these are row vectors. So you turn them into row vectors. Now we have A. We solve this. We row reduce the system to get this. Turn it back into our equations and solve for x and y, and we get this thing at the end, because we have we have these two free variables here. So if this is x, this is y, this is z, this is w, we end up with two more vectors here that are in the null space, and these are basis vectors for the null space, and so that is a basis vector for the orthogonal complement of W. We knew we would have 2 from the beginning because we're dealing in R4. We have 4 coordinates here, so we're in R4. This gives us a plane in R4, and so we need to have we have 2 more dimensions that we're dealing with. So we could have known from the very beginning that we were looking for 2 vectors. So the orthogonal decomposition theorem. So if we have a subspace of Rn, then any y in Rn can be written uniquely as the projection of y onto the subspace and a piece that is perpendicular to the subspace. So the projection will go into the subspace. The perpendicular is the piece that comes out that's perpendicular to the subspace. So and we can simplify that by saying, well, the perpendicular of W of y is in the orthogonal complement. The projection is in the subspace. That's what I was trying to say before. And if you have a basis that is orthogonal, this is key, it has to be orthogonal, then you can easily figure out exactly what these 2 vectors are. You can find the piece in the subspace and the piece that's not in the subspace. If they're orthogonal, then these are just projection formulas, and you just do the projection of y onto each of your orthogonal, each of the basis vectors. And since they're orthogonal, you can just treat each one independent. If they're not orthogonal, that won't work. So, and then once you get the projection of y onto the subspace, then you can just subtract that from y, and what you have left is the piece that's in the orthogonal complement of W. This is, yeah, let's look at this to help make sense of what's going on. So here's our y right here. W is this blue plane, and so you can see the projection of W, the projection of y down to here. So we have this purple line, and we also have this purple vector, and we also have a projection onto this line, because this line right here, that is perpendicular to the subspace. That's what that 90-degree piece is saying right there. So this is in y complement, and and this is in the orthogonal complement of W. What this is saying is we can decompose y into two special vectors, and those two pieces are the piece inside the subspace and the piece that's perpendicular to the subspace. So these two, if you add them together, you get y. This is the geometry, the same geometry we were talking about when we were doing regression, and we were trying to find the closest point in a subspace, and we were projecting that line down. Like the coefficients here in this of these basis vectors for the subspace, those are regression coefficients. So the math is, this is the same geometrically. This is the math of the mathematics of regression. The problem with regression is you usually don't have an orthogonal basis for regression, so it's not that you have to use those normal equations that derived. You can't use this really slick method. So usually, and just again, your basis vector has to be orthogonal. Your basis vectors have to be an orthogonal set. So this U1 and U2 are an orthogonal set. They don't span all of R3. They're in R3 because we have 3 coordinates. They don't span in all of R3. Now we're going to try to find those the projection, these two special vectors that we talked about up here. If we're given a random vector, can we project it on into the subspace of W and find the piece that's perpendicular? So to do that, since we can easily find the piece in, we can easily find the projection of it, is because we're dealing with an orthogonal basis by using these projection formulas. So so just using the projection formulas, we project this onto U1, we get this times U2, and you punch it out, and you get this. So we're adding these vectors together. So because you can see this purple vector down here that's almost all gone now. It's really purple. See? We're finding how much we're finding this piece, and then adding them together to get this vector down here, and it's part of the vector we need. It's the vector that we need that's in W. So that's where the adding comes up, because we're adding this piece and this piece, and we get that one. So now, how do we find that perpendicular piece? We just subtract it from this one, and we subtract it from y. That's y. Subtract the projection onto the subspace. We get this. And look, if we actually go back and do the dot product with this, look, you get 0. Dot product with this, look, you get 0. So it really, you can test to show that it is perpendicular. I shouldn't have a equal there anymore. Okay. So this works for the key thing in this theorem, this next theorem here, is that you can do this for V in any Rn. So if you've got a subspace of Rn and any V in Rn, then you can write it as, you can write its component in W and its component in the orthogonal complement of W, and those are unique. There's only one way to do that. This is something I mentioned before, like about we only have n dimensions to work with. So if we have if we're in R3 and W is a subspace of R2, then the orthogonal complement is going to be a one-dimensional subspace. So, and this is one we've seen before, the rank theorem. So the rank of A plus the nullity of A is n, and this is connected to this one here, right? The rank is going to be the dimension of W, and the nullity, because this is like, yeah, the nullity is the dimension of your null space, and the null space is the orthogonal complement of the row space of A, and the row space of A is going to span the number of dimensions that's equal to the rank. So that's where that connection is. All right, long video today. I'm really sorry that I struggled so much getting through that.